but just know that I am recording this. So I'm going to talk about the normal distribution today. And these should be the last thing you need to take your test 2 if you haven't taken test 2 yet. Again, test 2 is due by 4/16, so make sure that you're aware of that. And so we'll talk about the most important distribution to statistics, which is the normal distribution, all right? And it's defined just like the binomial is defined by 2 parameters. From the binomial, we talked about N and P. We talked about the number of trials, the number of fixed number trials, and the probability of success. The normal distribution is also defined by 2 parameters. And here's what's going to happen on this test. You're going to have a binomial, you're going to have binomial problems, and you'll also have normal problems. You can always tell the difference by what information is given to you. And in particular for the normal distribution, it'll give you 2 things. It'll tell you what the mean is. So we say the 2 parameters here are going to be, we say that X, the random variable X, follows a normal distribution with some particular mean mu and the standard deviation sigma. So we're going to talk about those 2 things, the mean and the standard deviation. Can y'all still not hear me?
I can hear you now.
Okay, cool. Good. Can everybody else hear me?
Mm-hmm.
All right, good. So, no, I have this thing I don't want to see. All right. And for the curve, we're going to draw a lot of normal curves. And these things right here are what we call normal curves. So these are all our different normal curves. We're going to draw a lot of them. And when we draw those normal curves, we're always going to put the mean, this mean value, at the center of the curve. So in this distribution, the mean is at the center of the curve. And what else? We talked about this with the empirical rule. When you draw these curves, there's always 6 standard deviations underneath the curve. And it's 6 standard deviations because you have from the mean at the middle, you have 3 to the right and 3 to the left. And remember, standard deviation is basically where it starts to drop it on each one of these things. So we're going to develop special properties for this curve, though, right? And here there are 3 properties we're really going to talk about. And the first thing you need to know is that the distribution is what we call symmetric. And remember, in a symmetric distribution, the tails are equal on both sides. And then in a symmetric distribution, the most important thing you need to know is that the mean is equal to the median. All right. And then it's symmetric and unimodal. Kimberly. Sorry. The distribution is symmetric and unimodal. And unimodal means that you only have one peak, and the peak of this always occurs at the center. So the other thing you need to know is that the tails of the distribution are asymptotic.
Yeah.
And that means this, when I say the tails are asymptotic, these tails right here on this distribution, they want to extend forever in this direction and forever in this direction, and they'll never touch the bottom of that curve, but never touch. So what that really means is that they extend for everyone to, on the left-hand side, it goes to negative infinity. Mm. And on the right-hand side, it goes to positive infinity. Now, this is going to matter when we start doing calculator calculations. And that's because our calculator doesn't have a negative infinity or a positive infinity button. So we're going to have to set what we call bounds in a few. And when we set our bounds, we're going to call negative infinity, just for our calculator's sake, we're going to call it negative 99999. A whole bunch of 9s back here. It doesn't really matter how many you put. You just need a lot of them. And what that tells me, I'm dealing with a very small number. And over here, we're going to call positive infinity positive 99999. And what that means, you're dealing with a really big number. And the reason we need that is because our calculator, like I said, our calculator doesn't have those buttons, negative infinity or positive infinity. So it needs a number to approximate with. And then the last thing you need to know is this: all of the area underneath this curve, because we're dealing with probability, and anything in probability, all of the total values in a distribution, they always add to 1. Well, the area is the same thing. All of this area is equal to 1. And what that allows us to do is that allows us to apply probabilities to this now. So that's what we're going to talk about is how can we use probabilities to solve things with this curve. And essentially what's going to happen is we're going to mark off certain parts of the curve. For instance, if you look at the center of the curve right here, well, we're going to calculate area up to the center of the curve. So if I want to calculate area up to the center of the curve, because it's half the curve, I know it's 50% of the curve. And we're going to be able to do things like that. So we're going to be able to find areas in between different standard deviations, in between different values. But before we get there, let's make sure you understand the properties here real quick. So look at this first example, and it says, consider the normal curves A, B, C, and D below. It wants to know what is the mean of each curve. Well, to determine the mean, we can look at the curve for A first. If you look at A, the mean always sits in the middle. So my mean here on A, the mean of A is equal to 2. If you look at the other 3 curves, all of their middles occur at the same number. So they all have the exact same mean. So the mean of B is equal to the mean of C, which is equal to the mean of D, and they're all equal to the value of 0. So the first thing you need to realize is this: these curves are not unique in terms of their means. They can have the same mean, but what makes them different is going to be now their standard deviations. And again, the standard deviation is where it starts to drop at on these curves, all right? So if we look at the first one, which curve has the smallest standard deviation? Well, to tell us something is a small standard deviation. What you're looking at is how spread out is the curve. The more spread out the curve, the wider the curve is, the larger the standard deviation. The tighter the curve, such as this blue curve right here, the smaller standard deviation. That's because you're trying to pack more information inside of there. So standard deviation of the one that has the smallest standard deviation is going to be the tightest curve, which is curve B. And that's because it's the tightest or the narrowest. The curve that has the largest standard deviation is the one that's spread out the most, which would be curve D. And that's because it is the widest or the fattest, if you want to look at it like that. So the fatter the curve, the more spread out it is, the bigger the standard deviation. The tighter the curve, the smaller standard deviation. But what makes these curves different are going to be where their means and where their standard deviations lie. Hey, I'm sorry, I hear a lot of background noise. My daughters just woke up and they're going to be in this video. So I apologize for that. Look at example 2. It says estimate the mean and standard deviation from the graph. So on example 2, the first thing to find the mean, we always look at the center of the graph. So the center of the graph is sitting at what value? When you look down here, the center of the graph is sitting at 0. So the mean is equal to 0. To find the standard deviation from the graph, the standard deviation under the graph is approximately where it starts to drop at. Well, on this graph, it's hard to really tell where that is because you don't know if it's dropping here, is it dropping here, is it dropping here? It could be dropping at all those places that you may be thinking of. The thing you need to remember though is this, and it comes back from this information over here at the very top where it says that there are approximately 6 standard deviations under the curve, 3 to the left and 3 to the right. Because of that, then we can find the range of this curve. And it looks like it goes from -100 to 100. That's approximately. So that range is going to be from -100 to 100 is 200 because it's from here to here, from here, -100 to 0 is 100. And then from 0 to 100 again is another 100. So it's a 200. So to find the standard deviation, if the range is equal to 200, then the standard deviation sigma, we know that this range consists of 6 sigma underneath it. So we can take 200 and divide it by 6 standard deviations. And then we divide that by 6 standard deviations. We get 200 divided by 6. I get 33.333. So the approximate standard deviation is 33.3. All right. So this is just the first part about understanding the properties of the curve and understanding that the mean occurs in the middle. There's six standard deviations for each curve. The thing that make these curves different are their means and their standard deviations. If we understand that, the next part is going to come where we're going to start drawing these curves and finding probabilities now. In order to do that, here's what's going to happen. First part says, because there are infinitely many normal curves, they're all defined by their means and standard deviations. We're going to use what's called a single curve. We're going to use one curve. And here's the problem. Because you have so many different curves, we need one curve to base everything off of. And that single curve has a mean of 0 and a standard deviation of 1. And it's called the standard normal. It's called the standard normal. So we call this curve the standard normal. And the word standard in statistics, just like when we talked about the standard deviation, the word standard means average. So this is just a average normal curve. And in truth, the word normal in statistics also means average. So what this really is what we call an average curve. And what makes it special though is that the mean of this curve, remember the mean always sits at the middle, the mean of this curve is 0. And then every standard deviation on this curve is 1. And notice here you have 3 standard deviations to the right and 3 to the left. All right. And what I want to focus on is what we're going to call now our z-scores. We talked about z-scores in our first test, but a z-score is how far, it tells how many standard deviations above or below the mean of value lies. Remember, it's above the mean if the z-score is positive. It's below the mean if the z-score is negative. And we did this with, for instance, if you take a test and the average is a 70 and you score an 80, your z-score will be positive because you've scored above the mean. If you score a 60, your z-score will be a negative because you score below the mean. Now, they're both 10 away though. So one will be a positive z, the other will be a negative z, but they're the exact same distance away. And remember, to find a z-score, here's the formula we use. Z was equal to your x, whatever you score on the test, for instance, minus the population mean. So let's say everybody took a test, the average was a 70. Your score minus the population mean divided by the whatever standard deviation is. That gives me the formula for a z-score. And now, if we can associate a z-score with any number on this curve right here, we can put in a z-score anywhere on this curve now. We can find the area up to particular points in this curve now, using those z-scores. And we do that through what we call shading curves. And when you shade curves or when you deal with normal distribution, what you're going to see is it's going to tell you that something is normally distributed. When you see the words normally distributed, or anything that says normal, when you see the words normal, that means draw a curve. This means to draw a curve. And when you draw a curve, you always label the middle, label your center with the mean, and then you go from there. And there's 3 types of curves we're going to draw, and they're based off their shading. And so the first what we call a lower curve. In a lower curve, you're going to shade it to the left of whatever the value is. So you're looking at the lower tail. It's also called a left tail curve. And in these particular curves, here's how this works. We're going to use our calculator to find probabilities. So we're going to be introduced to a new function. Just like you were with the binomial, you have a normal function in your calculator. And let's go find that. So to find the normal function, that's what you're going to press. Just like the binomial, you press second, and you press bars. And then when you go through here, second bars, at the very top, you have 2 functions that say normal on them, normal PDF and normal CDF. For this function, remember in the binomial, the PDF meant exactly. For the normal, there is no such thing as exactly. We will never use this first function up here. We've never used the PDF. We always use the CDF. Always use the CDF. And for the normal CDF, here's what happens. The normal CDF is given by what we call the calculator syntax, which looks like this. The normal CDF is you have a lower bound, an upper bound, a mean, and the standard deviation. The lower bound is where the leftmost shading takes place. So in a curve like this, the leftmost shading is going to go this way. The upper bound is where the shading is stopping at. So right here is stopping at this Z value right here. Your mean, because you're on a standard normal, is always going to be 0. Your standard deviation will be 1. So when we set this up, here's how this works though. Because I just told you that the shading always goes where, on the left-hand side, for instance, on the left-hand side, it's where the leftmost shading is. Well, technically this tail runs forever. So because it runs forever, it'll be negative infinity. Our calculator has no negative infinity button, and because it doesn't have a negative infinity button, we're going to estimate this left-hand side using a value like this. -99999, a whole bunch of negative 9s. All right. So if we plug this into the calculator, we would do normal CDF. My lower bound would be -999. My upper bound is going to stop at whatever the Z-score is right here. In an upper curve or a right tail shade, here's what happens. Your leftmost endpoint or your lower bound is sitting here, but this time the shading goes on forever in this direction. So we're going to call that positive 99999. All right. And then the next one is what we call a between curve. And in betweens, your lower is here on the leftmost shade. The upper is here on the rightmost shade. And you're shading between two values. So we're going to practice this, okay? So look at the next examples. And we'll start there. It says, given the following score, the Z-scores, find the probability associated with each by first drawing and shading a correct curve. So I've drawn curves for you, but generally speaking, you draw your own curves. And this first one says, find the probability that Z is less than -1.28. So this sign is telling me which way to shade already. And all I have to do is go on my curve and locate -1.28. Well, -1.28 sits somewhere in between -1 and 2. So let's say that that's the Z -1.28. If I want to be less than that, which way do I shade? Well, I'm going to shade this to the left because that's all the values less than -1.28. So when I look at this curve, I can see that the lower bound here is -99999. It's going to go on forever to the left. And it's stopping at this -1.28. So my calculator, I would type in normal CDF. And again, we always use the CDF, never the PDF. The lower bound is -9999. The upper bound, -1.28. And the mean of every one of these standard normals, when you deal with this letter, anytime you see the letter Z, anytime you see the letter Z in statistics, the mean will always be 0. Standard deviation is 1. So all we have to do is go to our calculator now. And remember to get there again, second, bars, normal CDF, -99999. And you can put how many nines you want to be honest. You just want to put a bunch back there. I'd put at least 4. And depending on your mean, if your mean is 4 numbers, you need 5. If your mean is 5 numbers, you need 6. If your mean is 7 numbers, you need 8. So you always need one more 9 than whatever the mean is. So -99999. -1.28 is the upper bound. The mean is 0, and the standard deviation is 1. And when you type that in, here's the probability of a Z-score being less than -1.28. That's equal to 0.10. So about 10%. of the values are less than negative 1.28. If we look at the next one, this one says the probability Z is greater than 1.12. So again, locate 1.12 on the curve. Now, this one says to be greater than. If it's greater than, that means shade to the right. So we're gonna say everything to the right this time. So when I do this one, it'll say normal CDF. The lower bound. 1 point. This time your lower bound is, you can see is this value right here, which is 1.12, which is the Z value. 1.12. And the upper value, or the upper bound, is going forever in this direction. So we call that positive 99999. So back here, I'll put 99999. And again, I'm on the standard normal. So standard normal mean is 0, standard deviation is 1. And I'll go to my calculator again, second bars. Normal CDF, always the CDF, never the PDF. 1.12, 999, 0, 1. And so here's what I get there, 0.131. So I'll leave C for y'all to do, and I'll go down to D. D says find the probability that -2, that the Z value is in between -2 and +2. What this is really saying, by the way, is that what's the probability that your Z value is in between, or the probability, the amount of area between -2 and +2? Well, we already know from the empirical rule that within two standard deviations of this curve should lie 95% of the values. So our answer should be very close to 95% here. And let's go ahead and verify that using normal CDF. And here's how we do that. We can see that our lower bound, our lower Z score, is -2. So I'm going to do normal CDF. Normal CDF. And I get lower bound, -2. And then the upper bound, going up to my upper bound, that's going to be a +2. So I go from -2 to 2. The middle of the curve is at 0, standard deviation is at 1. So normal CDF again, lower bound, -2. And notice this time I'm not using the 9s because I'm actually bounded by 2 solid numbers. So -2 to 2, 0, 1. And I get this. Look at the value I get. It's 0.954, which is about 95%. So what we've done so far is we found the area on a standard normal using Z-scores. Now, the good thing about the normal curve, though, is that it applies to more than just Z-scores. And for any one of these type of problems, you can always make everything into a Z-score. But that is a lot more work than what we really need to do. Our calculators can actually do work without Z-scores. And let's see what these two problems are like right here. These are problems that don't require you to use a Z-score. You can actually do the problem without making everything into a Z-score. And so what I mean by that is this. Look at example 2. So the customer calling a call center spends an average of 45 minutes on hold during the peak season with a standard deviation of 8 minutes. Here's the keywords that you're looking for first off. It says, suppose these times are normally distributed. When you see that, that means draw a curve. You're going to draw a normal curve. And then they want you to find probabilities based off of that normal curve. So the first thing you're going to do with normal curve is, what are the mean and standard deviation? We write it like this: X follows a normal distribution with a mean of 45 and a standard deviation of 8. And my mean is going to be at the middle of the curve. So my mean here is at 45. That's the middle of the curve. The first question asks me, what is the probability that your call time, your hold time, is more than 54 minutes? We write it like this: the probability that X is greater than 54 minutes. That's what more than 54 means. So what you need to do now is locate 54 on this curve. Well, it doesn't have to be exact, but 54 is on the right-hand side of this curve for us. So we'll put it over on the right-hand side. And we'll say that this is 54. If I want to be more than 54, which way do I need to shade the curve to be more than 54? Where are the numbers more than 54 at? They're more than 54 to the right over here. And notice this is more than 54. It don't tell us where to stop at, so it's not bounded. So we know our lower bound is 54, and it looks like our upper bound is going on forever to, again, you have to give it a number, 999. So when I type this in my calculator, I'm going to type it in like this. It's normal CDF. My lower bound is 54. My upper bound, 999. You need at least 3 nines because you have 2 for your mean. So 3 nines, and you can do more. But now here's how this is different. We are no longer on the standard normal curve. We are on a normal curve with a different mean and a different standard deviation. And I know I'm not on a standard normal because it's not a Z anymore, so letter X I'm talking about. And because it's X, what I'm going to do now is I'm going to change these means to, I'm going to change the mean to the mean of the curve, which is 45, and the standard deviation of the curve, which is 8. All right. So here's the difference thing. Here's the difference now. Lower bound, upper bound, but now we've switched the mean to 45 and 8 based off the problem because this is not a standard normal. So in our calculator, what we would do, second bars, normal CDF, 54, 999, 45, and 8. You type that in, you get this. So the probability that it is greater than 54, that you spend more than 54 minutes is 0.130. Now, we could do this with a z-score. And remember, the z-score transformation is this right here. Z equals x minus mu over sigma. So I can use that transformation to do the exact same thing by doing this. I could find a z-score that says z is equal to, well, my x here is this number right here, 54, minus my mean is 45, divided by my standard deviation, which is 8. So if I do 54 minus 45, I'm gonna divide that by 8, I get this right here. So I get a z-score of 1.125. What that means is I'm putting this back on a 0-1 curve though. So the mean of this curve will be 0, and then 1.125 will fall here. And I want to be greater than that value again. So what I would do is I would do second bars, normal CDF. The lower bound is the z-score, 1.125. The upper bound goes forever in this direction over here. So that's a positive 999. The mean is 0, the standard deviation is 1. And look what I get. I get the exact same value. So your calculator can do it by skipping the z-score process if you want to, but you can also find z-scores if you want to. This just takes the z-score method takes more work, but it's the exact same thing. So look at the next one. They want to know less than 32 minutes. Again, draw a curve, which we already have this curve right here given to us. Less than 32 would be on the left-hand side of the curve. So somewhere out here, right? Let's say that's 32. Less than would be this direction. And notice again, the leftmost shading this time. It's on the left-hand side, so your leftmost shading is going to be negative infinity. We don't have a negative infinity button, so we need to give it a number. We call it negative 99999. And so we write this normal CDF. We want to find the probability that x is less than 32. Normal CDF. The lower bound, the lower shading runs all the way to this way forever. So it'll be negative 999. The upper bound, it's stopping at 32 now. Again, our mean is still 45 and our standard deviation 8. So again, our calculator, second bars, normal CDF, negative 999, upper bound 32, 45, and 8. Type that in, and I get this right here, 0.052. And then the last one says to find the values between 32 and 54 minutes. So now I want to be inside of these two values. Well, exact same process. So I'm going to do the probability that this time you want X to be in between 32 and 54. Here's how you write that. Your X is sitting in between those two values, 32 and 54. So you're going to go from 32, the lower bound is stopping at this value, 32, and the upper bound is stopping at this value, 54. So we do normal CDF, lower bound 32, upper bound 54. The mean is 45, and the standard deviation is 8. And when you do that, you get second bars, normal CDF, 32, 54, 45, and 8. When you do that, you get 0.818. All right. So every normal problem where you see the word is normally distributed, you should always draw a normal curve. You should always draw a normal curve. And the reason you're drawing the curve is because you want to see the actual shading taking place. So you know where your lower bounds are and where your upper bounds are. All right. Does anybody have any questions about this so far? We good? Y'all still there?
No.
Okay. Good, thank you.
Still here, no questions yet.
Okay, cool. So I'm gonna let y'all do it. I'll save example 3 for y'all to do on your own. But this is really a simple thing if you draw these curves. If you try to do it without the curves, you might get lost. Make sure you draw the curves. So that's finding area. There's another thing that we can do with this process where we reverse it. And what I mean by that is this: I'm going to give you an area, such as I'll tell you something's at a particular, and when I give you area, I'm talking about a percentile. So I'll tell you something occurs at a particular percentile. I want to know what is the particular value X that gives me that. So we're going to go backwards. So it says, so far we have found a probability. We found a probability that corresponded to a score. We can reverse this process and find a score given a specific probability or area. The area that is given is also known as a percentile. And we've talked about percentiles too a while back. But a percentile tells how much area falls. So percentile, if you're at the 90th percentile, for instance, you're telling me how much area falls at or below. The percentile is always at or below. And that matters here because the function we're going to use in our calculator is called inverse norm. And we're going to go backwards to find this particular X value that gives me this at or below value. But because it's at or below, this function only works when you calculate the left-hand side of things. It only calculates the left tail of things. So when you do this, you need to look at you're always going to look at the left tail to calculate. And your inverse norm function works like this. Here's the syntax for it. You want to give it a percentile, or a percentile also means give it a area. And it's going to be expressed as a decimal. So look here, you would express your area up here for this particular problem, the 90th percentile, as 0.90. And it has to calculate this. Now, if this is 0.90 though, the right-hand side is going to be the point, it's going to be 10%. Because you're 90% on this side, 10% on that side. So the curve always breaks off to where these two numbers should add up to 1. But for this particular function, you're going to go backwards and actually give me the X that corresponds here. And I mean, like in this problem up here, when I gave you this 54, you gave me the probability or the area, which was 13%, that corresponded right here. This is basically the top 13%. The 13 or the what we call the, if this is 13% on this side over here, back behind it is 87%. So this would be this value right here, 54, represents the 87th percentile. So you're going to be able to tell me, if I give you a percentile, you're going to be able to tell me a number that represents a percentile. So let's look at the example. The problem says that scores for police training tests are normally distributed. That word normally distributed means to draw a curve. And it has a mean of 50 and a standard deviation of 10. So X is normal with a mean of 50 and a standard deviation of 10. First question says, an agency will only hire applicants with scores in the top 10%. What is the lowest score you can earn and still be eligible to be hired by the agency? So the first thing I'm going to do is I'm going to mark the curve with my mean, which is at 50. So the mean is at 50. And I want to know what is the top 10%. Well, top 10%, will that fall on the right-hand side or the left-hand side? If you're in the top 10, you should fall on the right-hand side somewhere out here. So let's say that this is where the top 10 percentile is. So that's the top 10%. And I want to look for this value X that denotes that top 10%. Now, the problem with trying to do this in my calculator, though, is this. My calculator can only calculate what side of the curve again? The left side. It can only do the left side, left tail. So if I'm at the top 10%, I need to know the percentile that corresponds to that by looking at the, come back this way. I need to look at the bottom 90 percentile, the bottom 90. So this is the bottom 90%. So that means I'm looking for the value for the 90th percentile. I want the 90th percentile here. That's what I'm looking for. And so my calculator is what I'm going to do. Inverse norm. And inverse norm is located, here's how we get to inverse norm. We press second bars. If you look under the normal functions, normal CDF, you have the inverse norm function. That's the function I want to use now, the inverse norm. An inverse norm wants you to give it a percentile first. And our percentile is the left side, the left area to this side. So it'll be as a decimal, 90% is 0.90. Then it wants a mean. Well, the mean here is 50. I'm sorry. Hold on, second, quick second. 0.90, 50. And the standard deviation was given to be 10. So comma 10. Press enter. And here's the score that corresponds to the top 10%. So anybody that scored the 62.8 or better will be scoring in the top 10%. And we can always verify this, that this area represents 10% by doing what we did before we got here. And what I mean by that is, well, look, if this is the cutoff point, I want to make sure that 10% of the area is up here. So to do that, I would do second bars, normal CDF. I can see that if I'm looking at this value right here, here's my lower shade, which is at 62.8. And then it extends forever in this direction. So that's 999. The mean is 50. The standard deviation is 10. When I do this, if I did this correctly right here, this should be an area of about 10%. If you look here, you get an area of about 10%. So that I know that this value right here corresponds to the top 10%, because there's 10% of the area above that value. This answer also makes sense because if I want to be in the top 10%, I should get a number that is bigger than 50. If I get a number that's smaller than 50, for instance, some of you may have, when you do this problem, you may do this instead. You see top 10%, so you do 0.1, 50, and 10. 50 and 10. If you do that, you get 37.18. Well, 37.18 is going to be on this side, which tells me that I'm not doing something correct. So be aware when you do that. You can check this to make it make sense to you. 0.9, 50, and 10. And so we get the value of 62.8. Look at B. The next one says, those officers scoring below the 20th percentile. I'm going to draw a curve again. The mean is at 50. Below the 20th percentile. Well, the 20th percentile, and it's easy to know where percentiles are based off of the mean is at the 50th percentile. That's the 50th percentile. So the 20th percentile has to fall on the left-hand side somewhere over here. And I want to be below that value. So below that means shade to the left. So if you notice here, this is different than the one above, because up here we were looking at the right-hand side to get that value. Now I'm on the left-hand side. So this means that when I type this into my calculator, it's inverse norm. The lower bound, the 20th percentile, is already correctly shaded to the left. It's on the left hand, the left tail. So all I'm gonna do is type this in as 0.2. I don't need to change that to 0.8. Leave it as 0.2 because you're on the left-hand side. The mean is 50, and the standard deviation is 10. So second bar is inverse norm. .2, because I'm looking at the 20th percentile. 50 is the mean, standard deviation 10. And I get 41.58. So this value right here, value X is equal to 41.6. Does that answer make sense? Yes. Why does it make sense? Because it's on the left-hand side of the curve. So it should be less than 50, and 41.6 is less than 50. So I'll leave this last one for y'all to do, to give that one a shot too. If you want to try it, just try it. I think the answer to that one is 8 years, I think, 8 something. But give it a shot, try it out. Let me know if you have any questions with that. As far as everything else goes, I am done.